All right, to start off, I'm going to show you what we're doing here. I've got something over here. You can see some of the water coming out there. I've got it covered, but eventually it's going to come down to this black line, and then I'm going to want to use it as a projectile, and I'm going to use that right there as my target. Okay, so let me back up here. Okay, and here's my water. I need to have it up to this black line, so I'm going to put a little extra. Okay, so it's above the line, but when it gets to that line, I'm going to see where it hits. This is not going to be perfect. We'll do the best we can. Okay, it's going down, bam, somewhere in there, okay? But notice that's within a couple of centimeters. All right, so while it's doing that, let's go ahead and measure how far away that is. Notice this is just fuzzy physics because I have to do it quickly. So that's somewhere around 68 centimeters, and it's about 94 and a half, 68 centimeters. All right. Now let's use the numbers that we just got to actually figure out some stuff. So if I start over here, I have, here's the bucket on top, shooting water out, etc. We measured very roughly to be 68 centimeters. Way more helpful if I have someone helping me with that. So this equals delta x equals 0.68 meters in the x direction. We measured the distance to the ground to be 94.5 centimeters. I think that was right. It's close enough. Okay, and that would be delta h or delta y, how far it falls. Well, if we know how far it falls to the ground, we know we can figure out its time. Delta y equals VIT, or V naught t, plus 1/2 AT squared, and we're working in the y direction, okay? This is a negative 0.945. Again, our numbers are not going to be that good. So that's going to be 0. If it's starting off horizontally, it has no vertical velocity. Horizontal is not vertical, so that equals 0 plus 1/2, and I'm going to use negative 10 because, again, we're not going to the millimeter here. All right, so that gives me negative 0.945 divided by negative 5 equals t squared. T equals, let's pull out my handy dandy, really old calculator from college. I get 0.43 seconds. Again, our numbers are not going to be that good. We're going to be off just because I didn't measure that well. Now in the x direction, since it's at constant speed, since a equals 0, speed equals distance divided by time, and we're trying to calculate the speed. Our distance is 0.68 meters divided by 0.43 seconds gives me 1.58 meters per second. Is that correct? I don't know. We think it is. Now, let's imagine we have this bucket, okay? And we know, we believe that the water comes out at a speed of 1.58 meters per second. Well, if we were pretending that we were doing conservation of energy, we would say that mgh equals 1/2 mv squared. The m's cancel. And h would equal v squared over 2g, or 1.58 squared divided by 20, which would give me a height of, we'll square that, divided by 20 equals 12.125 meters, or 12.5 centimeters. Let's find out how high that water was from the hole. All right, so we look at it, and it's actually in the 14s. That didn't work out as well as we thought. Let me go explain why I believe that is. Here's the thought. Okay, this is what we expected, and what actual, I don't know, 14 centimeters, 14 and a half, whatever, okay? Now, if we take Bernoulli's equation, and we do our before equals after with Bernoulli's, which is pressure, pressure due to height, and pressure 1/2 rho v squared equals the same afterwards. Now, here's what we were assuming in my calculation. Up here, we were saying that this is a large container, and that the height is that the water was not moving. So we put V equals 0. Down here, we said H equals 0, if we call that our reference point, which is easy enough to do. Now, since this is open to the atmosphere, then the pressure here equals 1 atmosphere. This is also open to the atmosphere. This is 1 atmosphere as well. So the pressures cancel, or subtract 1 to the other side, they cancel. And what I was doing was rho GH equals 1/2 rho V squared. The rho's cancel, and we just get conservation of energy. This did a big assumption. It assumed that this equals 0. I don't think it actually equaled 0. Okay, so notice, let me pause for a second here as I get something ready. Okay, a little bit of reality check here. Notice that this side was bigger than this side. Okay, so our assumption here that this equaled 0 is not going to affect it that much. Somewhere over here we're missing something, which as far as I'm concerned could be that it was going faster than we thought it was. I don't really know, okay? But I was basically trying to get you to a proof of this, but unfortunately it doesn't work perfectly. Now, if I had a better chance to measure, I'm not sure how far off these numbers are. And if I had a way, if I could do some calculations and spend some time on that, I could. But I wanted to get to this conceptually. This is known as Torcelli's. I'm not sure if I'm spelling this right. Torcelli's theorem, that given the assumption that not moving, etc., that you can just use conservation of energy. But ours didn't work out perfectly, but it worked out all right, I guess. It was close.